Good day everyone. We are the Group 3 and we will discuss the Module 10, which is the LAN security concepts. So, in this lecture, we will learn how vulnerabilities compromise LAN security. Topics to be covered are endpoint security, access control, layer 2 threats, MAC address table attack, and LAN attacks.
We will talk about endpoint security. So, what is endpoint security? It is the practice of securing endpoints or entry points of end-user devices such as desktops, laptops, and mobile devices from being exploited by malicious actors and campaigns. Network attacks today. The news media commonly covers attacks on enterprise networks. Most likely, these attacks will involve one or more of the following. First is distributed denial of service or DDoS. This is a coordinated attack from many devices called zombies with the intention of degrading or halting public access to an organization's websites and resources. Second is data breach. This is an attack in which an organization's data, servers, or hosts are compromised to steal confidential information. Last is malware. This is an attack in which an organization's hosts are infected with malicious software that cause a variety of problems. For example, ransomware such as WannaCry, shown in the figure, encrypts the data on a host and locks access to it until a ransom is paid. So next topic is the network security devices. Various network security devices are required to protect the network perimeter from outside access. So the first device, named Virtual Private Network or VPN-enabled router, provides a secure connection to remote users across a public network and into the enterprise network. VPN services can be integrated into the firewall. So the next device is Next Generation Firewall or NGFW. It provides stateful packet inspection, application visibility, and control, a next-generation intrusion prevention system, and advanced malware protection and URL filtering. So the next is endpoint protection. Endpoints are hosts which commonly consist of laptops, desktops, servers, and IP phones, as well as employee-owned devices that are typically referred to as bring-your-own devices. Endpoints are particularly susceptible to malware-related attacks that originate through email or web browsing. These endpoints have typically used traditional host-based security features such as antivirus or anti-malware, host-based firewalls, and host-based intrusion prevention systems. However, today endpoints are best protected by a combination of NAC, host-based or AMP software, an email security appliance, and a web security appliance. Advanced malware protection products include endpoint solutions such as Cisco Advanced Malware Protection for Endpoints. Cisco Email Security Appliance. The Cisco Email Security Appliance is a device that is designed to monitor simple mail transfer protocol. The Cisco Email Security Appliance is constantly updated by real-time feeds from the Cisco Talos, which detects and correlates threats and solutions by using a worldwide database monitoring system. This threat intelligence data is pulled by the Cisco Email Security Appliance every 3 to 5 minutes. These are some of the functions of the Cisco Email Security Appliance. First is we have block known threats. Next is remediate against stealth malware that evaded initial detection. The third is discard emails with bad links. Next is the block access to newly infected sites. Lastly, encrypt content in outgoing emails to prevent data loss. So, in this figure, the Cisco Email Security Appliance discards the email with bad links. Makikita po natin na threat actor sends a phishing attack to an important host on the network. The firewall forwards all email to the Email Security Appliance. And the third is the Email Security Appliance analyzes the email, logs it, and if it is malware, discards it. Cisco Web Security Appliance. The Cisco Web Security Appliance is a mitigation technology for web-based threats. It helps organizations address the challenges of securing and controlling web traffic. The Cisco Web Security Appliance combines advanced malware protection, application visibility and control, acceptable use policy controls, and reporting. Cisco Web Security Appliance provides complete control over how users access the Internet. Certain features and applications such as chat, messaging, video, and audio can be allowed, restricted with time and bandwidth limits or blocked according to the organization's requirements. The Web Security Appliance can perform blacklisting of URLs, URL filtering, malware scanning, URL categorization, web application filtering, and encryption and decryption of web traffic. So, makikita naman po natin in the figure, an internal corporate employee uses a smartphone to attempt to connect to a known blacklisted site. So, in the figure, a user attempts to connect to a website. The firewall forwards the website request to the WSA. So, the WSA evaluates the URL and determines it is a known blacklisted site. The WSA discards the packet and sends an access denied message to the user.
Authentication with a local password. Many types of authentication can be performed on networking device with each method offering varying levels of security. The simplest method of remote access authentication is to configure a login and password combination on console, BTY lines, and AUX ports. The method provides no accountability and the password is sent in the plain text. Anyone with the password can gain enter to the device. This is a sample of how will you do it. Authentication with the local password, SSH, or secure shells, is a more secure form of remote access. It required a username and a password, both of which are encrypted during transmission. The username and the password can be authenticated by the local database method. This will provide more accountability because the user's name is recorded when a user logs in. And this is an example of how will you do it. This is a continuation of authentication with a local password. The local database method has some limitation. User account must be configured locally on each device, which is not scalable. The local database configuration provides no fallback authentication method.
AAA components. AAA stands for Authentication, Authorization, and Accounting. AAA provides the primary framework to set up access control on a network device. AAA is a way to control who is permitted to access a network, what they can do while they are there, and to audit what actions they perform while accessing the network. AAA stands for Authentication, Authorization, and Accounting. It's a framework used to control access to network devices. AAA allows you to control who can access a network, what they can do on the network, and keep tracking of their actions. This provides a secure and organized way to manage a network access. Authentication. Local AAA stores usernames and passwords locally in a network device such as the Cisco router. Users authenticate against the local database as shown in the figure. Local AAA is ideal for small networks. This means that users must authenticate using the credentials stored on the device. Local AAA is a method of authentication, authorization, and accounting that stores usernames and passwords directly on a network device, like a Cisco router. Server-based AAA authentication. With the server-based method, the router accesses a central AAA server. The AAA server contains the usernames and passwords for all users. The router uses either the remote authentication, dial-in user service, or terminal access control system protocols to communicate with the AAA server. When there are multiple routers and switches, server-based AAA is more appropriate. This method offers greater scalability, security, and flexibility in managing network access. Authorization. AAA authorization is automatic and does not require users to perform additional steps after authentication. Authorization governs what users can and cannot do on the network after they are authenticated. Authorization uses a set of attributes that describes the user's access to the network. These attributes are used by the AAA server to determine privileges and the restrictions for that user. These attributes can include user rules, groups, permissions, and more, and are used to ensure that users have access only to the resources and functionalities that they need to perform their tasks while keeping sensitive information secure. In summary, authorization governs a user's actions and access on a network, and it relies on predefined attributes to enforce access control policies.
Accounting. AAA accounting collects and reports usage data. This can be used for such purposes and auditing or billing. The collected data might include the start and stop connection times, executed commands, number of packets, and number of bits. A primary use of accounting is to combine it with AAA authentication. The AAA server keeps a detailed log of exactly what the authenticated user does on devices. This includes all exec and configuration commands issued by the user. The log contains numerous data fields, including the username, the date and time, and the actual command that was entered by the user. This information is useful when troubleshooting devices. It also provides evidence for when the individuals perform malicious acts. Accounting is when a user has been authenticated. The AAA accounting processes generates a start message to begin the accounting process. When the user finishes, a stop message is recorded and the accounting process ends. 802.1x. The IEEE 802.1x is a port-based access control and authentication protocol. This protocol restricts unauthorized workstation from connecting to a LAN through publicly accessible switch ports. The authentication server authenticates each workstation that is connected to a switch port before making available any services offered by the switch or the LAN. With 802.1x port-based authentication, the device in the network have specific roles like the supplicant, authenticator, and the authentication. Supplicant requires access and response to requests from switch. The authenticator controls physical access to the network based on client authentication status, and the authentication performs client's authentication. Client or supplicant. This is a device running 802.1x compliant client software, which is available for wired or wireless devices. When switch or authenticator, the switch acts as an intermediary between the client and the authentication server. It requests identifying information from the client, verifies that information with the authentication server, and relies on response to the client. Another device that could act as authenticator is a wireless access point. Authentication server. The server validates the identity of the client and notifies the switch or wireless access point that the client is or is not authorized to access the LAN and switch services. 10.3. or the Layer 2 security threats. Layer 2 vulnerabilities. Recall that the OSI reference model is divided into 7 layers, which work independently of each other. The figure shows the function of each layer and the core elements that can be exploited. Network administration routinely implements security solutions to protect the elements in Layer 3 up to Layer 7. They use VPNs, firewalls, and IPS devices to protect these elements. However, if Layer 2 is compromised, then all the layers above it are also affected.
Switch attack categories. Security is only as strong as the weakest link in the system, and Layer 2 is considered to be the weak link. This is because LANs were traditionally under the administrative control of a single organization. We inherently trusted all persons and devices connected to our LAN. Today, the BYOD and more sophisticated attacks, our LANs have become more vulnerable to penetration. Categories such as MAC table attacks. Examples include MAC address flooding attacks. VLAN attacks includes VLAN hopping and VLAN double tapping attacks. It also includes attacks between devices on a common VLAN. DHCP attacks includes DHCP starvation and DHCP spoofing attacks. ARP attacks include ARP spoofing and ARP poisoning attacks. Address spoofing attacks includes MAC address and IP address spoofing attacks. STP attacks includes spanning tree protocol manipulation attacks. Switch attack mitigation techniques. Solution. Description prevents many types of attacks including MAC address flooding attacks and DHCP starvation attacks. DHCP snooping prevents DHCP starvation and DHCP spoofing attacks. Dynamic ARP inspection or DAI prevents ARP spoofing and ARP poisoning attacks. IP source guard or IPSG prevents MAC and IP address spoofing attacks. These Layer 2 solutions will not be affected if the management protocols are not secured. The following strategies are recommended. Always use secure variants of these protocols such as SSH, Secure Copy Protocol, SCP, Secure FTP or SFTP, and Secure Socket Layer or Transport Layer Security. Consider using out-of-hand management network to manage devices. Use a dedicated management VLAN where nothing but management traffic resides. Use ACLs to filter unwanted access.
Recall that to make forwarding decisions, a Layer 2 LAN switch builds a table based on the source MAC addresses and receive frames. Shown in the figure, this is called a MAC address table. MAC address tables are stored in memory and are used to more efficiently forward frames. A MAC address table is a table stored in memory on a Layer 2 LAN switch that is used to make forwarding decisions. It contains the source MAC addresses of received frames, which are used to more efficiently forward frames. MAC address table flooding. All MAC tables have a fixed size, and consequently, a switch can run out of resources in which to store MAC addresses. MAC address flooding attacks take advantage of this limitation by bombarding the switch with fake source MAC addresses until the switch MAC address table is full. When this occurs, the switch treats the frame as a unknown unicast and begins to flood all incoming traffic out all parts on the same VLAN without referencing the MAC table. This condition now allows a threat actor to capture all of the frames sent from one host to another on the local LAN or local VLAN. Note: traffic is flooding only within the local LAN or VLAN. The threat actor can only capture traffic within the local LAN or VLAN to which the threat actor is connected. MAC address table is flooding is network attacking, in which a threat actor bombards a switch with fake source MAC addresses until the switch MAC address table is full. This causes the switch to flood all incoming traffic out all parts on the same VLAN, allowing the threat actor to capture all of the frames sent from one host to another on the local LAN or VLAN. MAC address table attack mitigation. What makes tools such as MAC-off so dangerous is that an attacker can create a MAC table overflow. Attack very quickly. For instance, a Catalyst 6.5 switch can store 1,332,000 MAC addresses in its MAC address table. A tool such as MAC-off can flood a switch with up to 8,000 bogus frames per second, creating a MAC address table overflow attack in a matter of a few seconds. Another reason why these attack tools are dangerous is because they not only affect the local switch, they can also affect other connected layer 2 switches. When the MAC address table of a switch is full, it starts flooding out all parts, including those connected to other layer 2 switches. To mitigate MAC address table overflow attacks, network administrators must implement port security. Port security will only allow a specified number of source MAC addresses to be learned on the port. Port security is a feature that can be used to mitigate MAC address table flooding attacks. It allows network administrators to specify the number of source MAC addresses that can be learned on a port. This limits the number of MAC addresses that can be stored in the switch MAC address table, thus preventing it from overflowing.
Moving on to LAN attacks. First, VLAN hopping attacks. A VLAN hopping attack enables traffic from one VLAN to be seen by another VLAN without the aid of a router. In a basic VLAN hopping attack, the threat actor configures a host to act like a switch to take advantage of the automatic trunking port feature enabled by default on most switch ports. The threat actor configures the host to spoof 802.1q signaling and Cisco proprietary dynamic trunking protocol or DTP signaling to trunk with the connecting switch. If successful, the switch establishes a trunk link with the host. Now, the threat actor can access all the VLANs on the switch. The threat actor can send and receive traffic on any VLAN, effectively hopping between VLANs. In a basic VLAN hopping attack, the attacker takes advantage of the fact that Dynamic Trunking Protocol or DTP is enabled by default on most switches. The network attacker configures a system to use the DTP to negotiate a trunk link to the switch. As a result, The attacker is a member of all the VLANs that are trunked on the switch and can hop between VLANs. In other words, the attacker can send and receive traffic on all of those VLANs. The best way to prevent a basic VLAN hopping attack is to turn off DTP on all ports and explicitly configure trunking mode or access mode as appropriate on each port. Next is the VLAN double tagging attack. A threat actor in specific situations could embed a hidden 802.1Q tag inside the frame that already has an 802.1Q tag. A VLAN double tagging attack is unidirectional and works only when the attacker is connected to a port residing in the same VLAN as the native VLAN of the trunk port. The idea is that double tagging allows the attacker to send data to hosts or servers on a VLAN that otherwise would be blocked by some type of access control configuration. Presumably, the return traffic will also be permitted, thus giving the attacker the ability to communicate with devices on the normally blocked VLAN. Double tagging occurs when an attacker adds and modifies tags on an Ethernet frame to allow the sending of packets through any VLAN. This attack takes advantage of how many switches process tags. Most switches will only remove the outer tag and forward the frame to all native VLAN ports. With that said, this exploit is only successful if the attacker belongs to native VLAN of the trunk link. VLAN attack mitigation. VLAN hopping and VLAN double tagging attacks can be prevented by implementing the following trunk security guidelines. First, disable trunking on all access ports. Second, disable auto-trunking on trunk links so that trunks must be manually enabled. Third, be sure that the native VLAN is only used for trunk links. DHCP messages. Dynamic Host Configuration Protocol servers dynamically provide IP configuration information, including IP address, subnet mask, default gateway, DNS servers, and more to clients. As you can see in the figure, it shows the process of DHCP messages. DHCP attacks. Two types of DHCP attacks are DHCP starvation and DHCP spoofing. Both attacks are mitigated by implementing DHCP snooping. The goal of the DHCP starvation attack is to create a DOS for connecting clients. DHCP starvation attacks require an attack tool such as Gobbler. Gobbler has the ability to look at the entire scope of leasable IP addresses and tries to list them all. Specifically, it creates DHCP discover messages with bogus MAC addresses. In a DHCP starvation attack, an attacker broadcasts large number of DHCP request messages with spoof source of MAC addresses. If the legitimate DHCP server in the network is touched responding to all the bogus DHCP request messages, available IP addresses in the DHCP server scope will be depleted within a very short span of time. Once the available number of IP address in the DHCP server is depleted, network attackers can set up a rogue DCHP server and respond to a new DCHP request from network DCHP clients. By setting up a rogue DCHP server, the attacker can now launch DCHP spoofing attack. This DHCP spoofing attack. A DHCP spoofing attack occurs when a rogue DCHP server is connected to the network and provide false IP configuration parameters to legitimate clients. A rogue server can provide a variety of misleading information, such as wrong default gateway. The rogue server provides an invalid gateway or the IP addresses of its hosts to create a man-in-the-middle attack. This may go entirely undetected as the intruder intercepts the data flow through the network. Next, wrong DNS server. The rogue server provides an incorrect DNS server address pointing the user to a nefarious website. And last, wrong IP address. The rogue server provides an invalid IP address, effectively creating a DOS attack on the DHCP client. When an attacker operates a rogue DHCP server, a user can blindly start a DHCP communication with the attacker instead of the legitimate DHCP server on the network. This could easily happen when the rogue DHCP server is closer to the DHCP client and replies before the legitimate DHCP server does. As a result, the attacker can perform a man-in-the-middle attack by assigning itself as a default gateway or DNS server in the DHCP replies sent back to the DHCP clients. This allows the attacker to intercept IP communication between the configured clients and the rest of the network. ARP attacks. Recall that hosts broadcast ARP requests to determine the MAC address of a host with a particular IPv4 address. This is typically done to discover the MAC address of the default gateway. All hosts on the subnet receive and process the ARP request. The host with the matching IPv4 address in the ARP request sends an ARP reply. According to ARP, RFC, a client is allowed to send an unsolicited ARP request called gratuitous ARP. When a host sends a gratuitous ARP, other hosts on the subnet store the MAC address and IPv4 address contained in the gratuitous ARP in their ARP tables. The problem is that an attacker can send gratuitous ARP message containing a spoofed MAC address to a switch, and the switch would update its MAC table accordingly. Therefore, any host can claim to be the owner of any IP and MAC address combination they choose. In a typical attack, a threat actor can send unsolicited ARP replies to other hosts on the subnet with MAC address of the threat actor and the IPv4 address of the default gateway. There are many tools available on the internet to create ARP man-in-the-middle attacks, including the Snip, Cain and Nabel, Ethercap, Yersinia, and others. IPv6 uses ICMPv6 Neighbor Discovery Protocol for Layer 2 address resolution. IPv6 includes strategies to mitigate neighbor advertisement spoofing, similar to the way IPv6 prevents and spoofed ARP reply. ARP spoofing and ARP poisoning are mitigated by implementing DAI. Address spoofing attack. IP addresses and MAC addresses can be spoofed for a variety of reasons. IP address spoofing is when a threat actor hijacks a valid IP address of another device on the subnet or uses a random IP address. IP address spoofing is difficult to mitigate, especially when it is used inside the subnet in which the IP belongs. MAC address spoofing attacks occur when the threat actors alter the MAC address of their host to match another known MAC address of a target host. The attacking host then sends a frame throughout the network with the newly configured MAC address. When the switch receives the frame, it examines the source MAC address. The switch overrides the current MAC table entry and assigns the MAC address to the new port. It then inadvertently forwards frame destined for the target host to the attacking host. STP attack. Network attackers can manipulate the spanning tree protocol to conduct an attack by spoofing the root bridge and changing the topology of a network. Attackers can make their hosts appear as root bridges and therefore capture all traffic for the immediate switch domain. To conduct an STP manipulation attack, the attacking host broadcasts STP bridge protocol data units containing the configuration and topology changes that will force spanning tree recalculations. The BPDUs sent by the attacking host announce a lower bridge priority in attempt to be elected as the root bridge. Note, these issues can occur when someone adds an Ethernet switch to the switch network without any malicious intent. An STP manipulation attack is when an attacker, hacker, or unauthorized user spoof the root bridge in the topology. The attacker broadcasts an STP configuration topology change BPDU in an attempt to force STP recalculation. The BPDU sent out announces that the attacker system has to lower bridge priority. The attacker can see a variety of frames forwarded from another switches to it. STP recalculation may also cause a denial of service or DOS condition on the network by causing an interruption each time the root bridge changes. CDP reconnaissance. The Cisco Discovery Protocol, or CDP, is a proprietary Layer 2 link discovery protocol. It is enabled on all Cisco devices by default. CDP can automatically discover other CDP-enabled devices and help auto-configure their connection. Network administrators also use CDP to help configure and troubleshoot network devices. CDP information is sent out CDP-enabled ports in a periodic, unencrypted multicast. CDP information includes the IP address of the device, iOS, software version, platform capabilities, and the native VLAN. The device receiving the CDP message updates its CDP database. To mitigate the exploitation of CDP, limit the use of CDP on all devices or ports. For example, disable CDP on edge ports that connect to untrusted devices. To disable CDP globally on a device, use no CDP run global configuration mode command. To enable CDP globally, use the CDP run global configuration command. To disable CDP on a port, use the no CDP enable interface configuration command. To enable CDP on a port, use the CDP enable interface configuration command. Note, link layer discovery protocol or LLDP is also vulnerable to reconnaissance attacks. Configure no LLDP to run disable LLDP globally. To disable LLDP on the interface, configure no LLDP transmit and no LLDP receive. To be sure and address these vulnerabilities, it is recommended that you disable the use of CDP on devices that do not need to use it.
A VLAN hopping attack is going to enable traffic from one virtual local area network to be seen by another virtual local area network. And this is without the aid of a device such as a router. This is a basic VLAN hopping attack. A threat actor is going to configure a host to act just like a switch. And then using that host, they're going to take advantage of the automatic trunking port feature that's enabled by default on most switch ports. This would be the modes of dynamic auto or dynamic desirable on the switch ports. The threat actor is going to configure the host to spoof those 802.1q signaling and those DTP messages so that the trunk will form between the host and the switch. With a successful trunk established, they're going to be able to send and receive traffic on any virtual local area network, effectively hopping between any VLANs that they want to connect through. With a VLAN double tagging attack, a threat actor is going to embed a hidden 802.1q VLAN tag inside of a frame that already has an 802.1q VLAN tag. What's going to happen here is we're going to have an attacker that's going to double tag a frame. For example, our attacker was going to build a message that's going to communicate from its current VLAN, which is VLAN 10, with a targeted VLAN of VLAN 20. With the attacker currently being on VLAN 10, they're going to build a frame that's going to have an external VLAN header on it of VLAN 10, and then an internal tagged VLAN of VLAN 20. When that message is sent up to the first switch, our first switch is going to see the external outside header of VLAN 10. It's going to strip that off and then send this traffic on its way to any device running in VLAN 10. Well, the switch sees that VLAN 10 is also the native VLAN, so it's going to remove the VLAN 10 header and move it across the trunk link. Now, as that frame moves across the trunk link, the first header of VLAN 10 was removed. And now the internal tag, which is the VLAN 20, that still exists. This second switch is going to receive that frame, and it's going to strip off that VLAN 20 header, and then it's going to forward it out any VLAN 20 ports, which includes down to that targeted host. This is effectively allowing our threat actor machine on VLAN 10 to communicate to the target on VLAN 20 using a double tag. Now, VLAN hopping and this whole idea of VLAN double tagging, they can both be prevented by putting in a couple security guidelines. Number one, we should get rid of trunking on any access port that goes to end devices. Also, the whole idea of auto trunking, using things like dynamic desirable and dynamic auto, that should be disabled. We should use a manual static trunking as needed. Also, native VLAN should only be used on trunk links, and that native VLAN should never span to a user device. For instance, in this scenario only works when the threat actor is on the same VLAN as the native VLAN between our switches. DHCP is a powerful tool for easy dynamic addressing across our networks. but it can also be a powerful tool for malicious threat actors that want to have some fun with a network. So, quick recap of DHCP. We have DHCP servers that are going to dynamically provide addressing for us. That addressing includes IP addresses, subnet masks, default gateway, DNS servers, and even more with DHCP options to our clients. The typical conversation with DHCP goes back to DORA. Discover, offer, request, acknowledge. Our client's going to send a broadcast message, which is a discover. A server is going to hear that broadcast message and respond with a unicast offer of, this is what I can give ya. Here's some addressing info. The client receives that offer, it's very excited, and it sends out a broadcast of, I accept the offer you sent me. That server finishes it up with a unicast saying, you like the offer, I'm glad, I acknowledge. And then the lease is complete regarding the client taking that addressing info. It sounds easy enough, but now let's bring in an attack. Now it sounds funny saying it, but there's two common types of DHCP attacks. We've got the DHCP starvation attack and DHCP spoofing. With DHCP starvation, the goal of the threat actor is to create a denial of service for your connecting clients. What would happen is the threat actor would gobble up all of the usable DHCP provided addresses. The easiest way to go about this is having a threat actor using a client machine that's cycling through source MAC addresses very quickly, and for each source MAC address gobbling up an available IP address being given by your DHCP server. When all the addresses are taken from the DHCP server, there's nothing to provide the legitimate clients. On top of that, there's the DHCP spoofing attack. Imagine having a threat actor putting out their own DHCP server on your network. And when your clients use the whole DORA process and they broadcast out for a discover, and then there's the offer, the request, but then your rogue DHCP server finishes the conversation with the client with an acknowledgement providing wrong default gateway info, incorrect DNS servers, as well as even wrong IP addresses for the clients to use. Effectively, your legitimate clients cannot communicate on the network. So we have to prevent this by using safeguards and implementations for security. Address Resolution Protocol is a powerful protocol on our networks that allow our networks to function. With ARP, we're talking about having a known IP address being mapped to an unknown MAC address. And this is being used all the time with our devices on the network. Now, a client can send an unsolicited ARP reply, which is known as a gratuitous ARP. It's really a broadcast that we have a specific IP address that is mapped to a specific MAC address. Now, the problem is when someone sends out a gratuitous ARP as a broadcast, other devices, which should be hosts as well as network switches, are going to store that MAC address and IP address combo in their ARP tables and MAC address tables. This is an issue because a threat actor can send a gratuitous ARP message with spoofed information inside of it. This effectively allows any host to claim to be the owner of any IP address and MAC address combo that they want to. So let's talk about it. Here in our graphic, we've got PC1, PC2, and R1. They all have ARP caches that are up to date and correct. But what's going to happen here is PC2, the threat actor, is going to send out a gratuitous ARP. And that gratuitous ARP is going to claim that 10.0.0.1, the IP address of the router, is reachable by using MAC address all Cs, which is the MAC address of the threat actor. Also, the threat actor PC2 sends out a gratuitous ARP claiming that 10.0.0.11, which is the IP address of PC1, is reachable with MAC address all Cs, which is again the attacker. So what's going to happen here is when PC1 sends data to the 10.0.0.1 IP address, it'll be sending it at layer 2 to the attacker, which is all Cs. When the attacker receives this data, it'll be using it as a man-in-the-middle attack. When the router responds to 10.0.0.11, the router will be responding to the layer 2 target, the MAC address of all Cs, which again is going to be the threat actor. So what it comes down to is exactly this. PC1 will want to send data to 10.0.0.1, and to do so, it'll send it to the MAC address of all Cs, which is PC2. PC2 forwards that data onto the router. The router will send it outbound to where it needs to go. As the router responds back to that 10.0.0.11 IP address, it'll be responding back targeting all Cs, again the MAC address of the threat actor. This is a beautiful man-in-the-middle attack. Spanning tree is a protocol that is on by default on our Cisco switches. Its job is to provide us redundant connections while maintaining loop-free pathways, and it does it great. But the problem is threat actors can utilize spanning tree to actually change the topology of your network infrastructure. Now, the way they would do this is based off of logical, not based off of physical connections, but they would make their host appear as a root bridge. To do this, they would be sending out bridge protocol data units, which are spanning tree layer 2 messages, and these messages will include a priority of something insanely low, such as 0, for example, here in our graphic. By sending out these spanning tree messages saying that their priority is insanely good, the network infrastructure will view that threat actor's host, which is pretending to be a switch, as the root bridge, and they will all find the best way to reach the root bridge, which means they'll be dropping their main connection between each other and connecting through that switch itself. This allows the threat actor machine to pretty much act as a man-in-the-middle style attack and to be able to see all network traffic moving across this network domain. Cisco Discovery Protocol is a Cisco proprietary Layer 2 link discovery protocol. This thing is amazing. It can be used to verify Layer 1 and Layer 2 connectivity. And the cool thing is it's on by default on all Cisco devices. Now, on that same point, it can be insanely scary that it's on by default on all devices because it's used to automatically discover other CDP-enabled devices that are directly connected. This can even be used to auto-configure some of their connections. Now, while CDP is extremely useful in network troubleshooting, our threat actors can use it to easily discover network infrastructure vulnerabilities. For example, the CDP information that's being sent out, it's being sent out periodically and as unencrypted broadcasts. This information that is periodically sent out and sent out in an unencrypted format includes the IP address of the Cisco device. It includes the Cisco Internet Networking Operating System version. It includes the platform, and even based off of the capabilities of that model of the device. It even includes VLAN information and more. So here's a graphic that pulled off of a protocol analyzer showing a CDP message and ripping it apart in this unencrypted, unsafe protocol reaching out to our end devices. So how can we stop our end devices from receiving this periodic unencrypted CDP laden full of info of greatness? Well, 2 commands. We have no CDP run. No CDP run is put in the global config mode of your device, and that will turn off CDP everywhere on your Cisco device. Or you want to leave CDP on for those inter-network device connections between Cisco devices, but just off on the user interfaces. That would be the command no CDP enable. That's in interface config mode, and that's what you use on your interfaces connected down to end devices. We also have LLDP, which is Link Layer Discovery Protocol. It's a ventral neutral flavor of CDP. This is also vulnerable to recon attacks. We can turn this off globally in our global configuration mode using the no LLDP run command. As well as if you want to do interface-specific commands, we can use no LLDP transmit and also no LLDP receive, respectively.
And that's all for the Module 10 LAN Security Concepts. Thank you.